Today's talk will be about the factored approach to solving Dec POMDPs. Work done by me, Ronen, Brafman, and Shani. So the table of contents here will be, first we'll start over with a high-level overview of the algorithm and our setting. Next, we'll go a little bit deeper into the algorithm itself, which is called the DMAP, Factored Distributed Multi-Agent Planning. And then we'll go over some empirical results and talk about future research. Okay, so we'll start with the overview. So FDMAP, Factor Distributed Multi-Agent Planning, a novel approach for solving Dec POMDPs using factorization to several POMDPs. So our goal here is mainly by receiving a Dec POMDP, we want to split or decompose the Dec POMDP at hand to several POMDP problems. It represents an agent's share of the problem. Then by solving the problem from each agent's perspective, meaning that we solve each of these POMDPs at hand, we can then generate a set of policies, one for each problem, which if then coordinated can ultimately solve the required Dec POMDP, which is what we will refer to as the original problem, the Dec POMDP input to the algorithm. Okay, so we are starting off based on definitions. The Dec POMDP of an agent is a tuple, so we have a state space S, the joint action space, which is again decomposed to the actions of each agent, refers to AI. T is the transition function. We do not assume it is deterministic or anything. R the root function, omega the observation space, which is again can be decomposed to the observations of each agent. And O is the joint observation function. So again, our joint observation function is inputted with which state, the joint action, and the joint observation. And finally, we have the initial state for each agent. Well, in fact, we assume that all agents have the same initial space. So they all start off with an identical view of the state. So in our setting, we're using factor Dec POMDP, which is really similar to the variant proposed previously. So basically, the main change is that we factor the state space, which is represented here by S, to state variables, where each state variable represents some component in the world. And again, each state variable can receive a value, and the state is composed of the composition of all of these variables. Okay, so this was the high-level overview. Now we'll get into the algorithm itself. So first, we'll go over a high-level structure of the algorithm. So we're given with a factor Dec POMDP denoted by P. And then we generate and solve the team problem, P-team, which we'll show in a minute now, resulting with the team policy, raw team. So we've received the Dec POMDP problem P. We changed it a bit and created the team problem P-team, which again we'll show again very soon. And then we have a team policy which actually solves the team problem, which is denoted by raw team. Then by using that original problem P and our team policy or team solution, we generate different single agent POMDPs, which again are the factorization of the original problem, which are denoted by P1 to Pn, one for each agent. And then we solve each of these PIs and obtain a policy matching it rho. Finally, we align those policies that resulted from each solution. And these alignments allow us to achieve the final policies for each agent. So we end up with a set of policies, which if we apply to the distributed version, which is the original Dec POMDP P, can actually solve the problem. So we'll now go into detail over each of these steps. So first for the team problem. We received the original problem P, and we want to construct a team problem, which is basically taking the original Dec POMDP problem P and allowing for full communication, or equally allowing for a master agent to see the observations of all agents after each action. which is exactly what's stated here. So once we have the team problem, P-team, we want to solve it. And of course, solving the team problem is much easier than solving the original problem, P, because now we don't have the problem of agents not being knowledge of what other agents do, or to be exact, what other agents receive as an observation. So again, the team problem is a POMDP, since we decentralized we centralized the agents to be a single master agent, so-called. Then we solve that policy to obtain solve the problem to obtain the team policy. And we represent policies as directed graphs. Each node represents an action, and each edge represents an observation. So I just want to make a small example, which will go a bit deeper later on. So these are two policies. So for example, if we consider the second action here, which is sent by agent 1 of box 2, we can see that after it's invoked, we can either see yes, this stands for the observation of the second agent, for the first agent, so we can either observe yes or observe no. So either one of the branches go to a different action. So go back to. Okay, so this is the policy, which is again a directed graph. So where we at? We have the team policy, as we just saw. And our next objective, as we saw in the high-level overview of the algorithm, is to generate these single-agent problems. In these problems, the agent will be explicitly rewarded for executing actions that influence other agents. That means, as we'll see right now, is called the public aspect. So if we have the team policy, or let's consider this decentralized problem, we have many planning that each agent can do for its own, which strictly doesn't affect any of the other agents. But the main problem is the coupling between the policies, which is again quite similar to what was presented before. So this will be considered as the public aspect, the one that affects other agents. And to identify this action or aspect, we need to examine what our public and private variables and actions are, which is what we'll do now. So what is private and public? State variables, as mentioned in the factor POMDP setting, can be relevant to several agents. When a variable is relevant to a single agent only, other agents indeed may ignore it in their planning. So if we have, for example, the location of the agent, other agents may not really care about it. They only care what the agent finally does. For example, if it manages to push the button. To make coordination easier, we narrow the agent sites only to parts of the world that are relevant to them. So if we take an agent, and again, as we said, for example, the location of another agent is becoming irrelevant, we don't want the other agent to even look at it. So we want to narrow its state space, or not exactly state space, but its planning consideration to the variables relevant to it only. And by that, we disregard the relevant variable. So this raises the problem of how to determine if a state variable is relevant to an agent, because this is not strictly straightforward. So now we'll go over definitions of what is private and public. So we say that a state variable is relevant to an action if it either influences or affected by the action. So we can think of an action, again, I'll go back to the box pushing example because it's what we finally use. So we have an action of push. So both the box location and the agent location influences the action of an agent pushing a box. And what is affected by the action is only the box location. Then a state variable is relevant to an agent if it is relevant to any of its actions. So this was the first part where we say when a variable is relevant to an agent. Then we just generalize this to a state variable relevant to an action, and we generalize this to a state variable being relevant to an agent. Finally, we say, given these relations or affinity connections between them, that the state variable is public if it is relevant to several agents. Otherwise, it is private. So we have a variable. It can either be relevant to two agents, then it will be public, for example, a box location. Or differently, we can look at an agent location, which is relevant only to the own agent. So it becomes private since it's relevant to the other agent. Finally, an action is public if one of its relevant variables is public. So we have an action, we have the set of its relevant variables. We can now ask on each variable whether it is private or public. And if one of them is public, we say that the action is public. And again, otherwise it is private. Now we're real. We can identify the public actions of an agent. So given an agent, we can go over its actions and say which is private and which is public, which is what we wanted previously. Now that we have that notion, we can analyze the team policy and extract the public part for each agent by, again, identifying those public actions. And then to analyze the team policy, which is a matter of its own, we sample it. So what does it mean? So recall that we have the team policy and the problem itself. So we simulate the team policy many times, and many times refer to, as can be seen in the paper, to concentration bounds, which say exactly how many times we would want to sample. So we simulate the team policy many times to obtain a set of traces, and each such trace represents the projection trajectory of the agents involved. So, for example, if we take the team policy and simulate it once on the problem, we can see that we have a certain action, then followed by an observation, and the result. So on and so forth. The state changes, and then again, we apply an action and go over this process again. So after we do that, we have a set of traces accompanied with the policy and the problem. And then we can analyze the traces, since they are much more explicit of the team policy itself, the extractive representation of the executed actions. So we call that, in fact, we'll be interested in the public actions. And each such action that we're interested in will be referred to as the context action, or CA for short. So a context action will be, as we now see, a pair of an action in the context. So we can think of looking at the traces. We have an action which is applied in a certain state. Now the context is some projection of it that basically manifests the idea of what we said previously, which is narrowing the agent's perspective. So we're interested in exactly those CAs, or context action, of actions that influence other agents. Basically, the ones that match any public action of the agent. The context is constructed with respect to the operating agent. So we have a certain action, which is an action of an agent, and we do such projection, meaning transferring the state to the context by looking at the action together with the agent. So as we said here, we take the state and project it into two parts. So we have the private variables of the agent that operates the action, and the public variables, which are general to the problem. So this is the part that takes into effect the idea that we need the agent to understand how to project its state. And this is what is relevant to the whole problem, the public variable. And then by transferring a state to a context, we can, given a state, ask if the state matches the context. So what we would want is that the state agrees with all the projected state variables of the context, which, if we think again of the example, can be a context in which the first agent applies some action and we project out or only project onto the agent's location and the box's location. And then any state that matches the own agent's location and the box's locations will match the context, where we really disregard the location of the other agents. So to summarize the single agent problem, to summarize the policy analysis, we took the policy and extracted those CAs. Now we want to use that information to construct the single agent problem, in which each agent will try to achieve its public parts of the team policy rather than the original goals, because we wanted to only apply the actions that influence other agents. To generate this problem, we again use the original problem and the traces, which is what we just produced. And this process contains two major parts. So one is qualitative and the other is quantitative. So in the qualitative part, which we'll again look at here, we filter out the coagents present from the original problem. The quantitative one, we want to reshape the reward function to incentivize the new goals. So let's go a bit deeper into each. So about filtering the coagents presence, we remove sensing of other agents, which is essentially saying, okay, we have an agent and we don't want to allow it in a single agent to be able to sense for other agents because it's completely irrational to do. We remove actions of other agents that weren't used in PTM. Again, this is important because we do allow our agent to perform other agents' actions, but it's only as a simulation. So we allow it to simulate other agents' actions, but we don't want it to apply any actions that weren't used at all. And finally, which is the possibility to turn private actions of other agents to deterministic. So this is only optional if we assume that the actions have one positive and several negative outcomes. So we can basically simplify the agent's planning of other agents by turning the private actions to deterministic. So it doesn't have to reason about them too much. And the second part, which is the quantitative part, is done by altering the reward function to reward our context actions. So we aim at achieving two properties. We want to first incentivize the agent for achieving public parts of the team policy. So this is exactly what we said about having the CAs and the idea of giving enough rewards so the agent will find it beneficial to do that. But we also need to eliminate the need of the agent to accomplish the original goal. Because if we'll introduce both parts, also incentivize it for achieving the public parts and the original goal, it could just do them both, and it's certainly what we don't want. And more specifically, we do this in several steps. So first, we remove the reward given for the original goal, which exactly matches the second point here. Then we reward the execution of agent CAs found in the traces. And finally, we penalize out of context execution of actions. This relates more to the traditional idea of reward shaping because we don't want to allow the agent to perform any other actions, even if it's his own or the other agent's. Because then we could get into situations where the agent could just abuse the reward function. It would create kind of cycles of reward for him, which could just produce infinite reward basically. Okay, so now that we have the single agent problems, which recall that we both reduce the problem to match the agent's perspective by filtering out the coagent's existence, and we reshape the reward function to only make it beneficial for him to apply those context actions. And now having the set of POMDPs, P1 to Pn, we can solve them basically to obtain the raw policies, which we'll now see why we call them raw policies. So after we solve them, we obtain the set of policies, but we're not really done. So the agents perform a superficial planning for other agents. As we said, for example, if we determinize the private actions of other agents, the agent could completely apply them in a single time and just assume they happen without really reasoning about what actually happened. And so to handle that, we need an alignment process. So as we said, an agent policy might contain some of other agents simulated public action and private actions to be frank. So the appearance of each action represents the timestamp in which the agent thinks its co-agent will apply the action. But in fact, we need to postpone the thought, that idea of, okay, the other agent is applying the action I need now to match the co-agent's actual behavior. And we do so using no-ops. We want to just postpone the action far enough so the agents will be coordinated. So for that, I'll again go back to the previous example, which we can see an effect of the alignment practically here. So we have a collaborative action that where both agents push a box left. And let's say that this agent planned it to happen on the fourth timestamp because it had to do some actions before, but the second agent just waiting in the place for the box needed to be pushed. Let's say only a single timestamp because it said, okay, then it will push it very fast since I don't really plan for it, and applied it, let's say, in the second timestamp. So the alignment would be with respect to when we align, that policy, we'll say, okay, we have this action here in the fourth timestamp. In the other agent's policy, it will appear in the second timestamp. So we want to postpone it to be in the same place, which is the fourth. So we had here the note.
Excuse me.
Yeah.
You're running out of time?
Yeah, I'm almost done.
Okay.
1 minute. So to fastly go over the empirical results, we did a collaborative box pushing problem, which in which the agents had to push light and heavy boxes in uncertain environments, and they had to coordinate and sense for the coagent outcome. So we'll go over the interesting results, which is basically this one, in which we have competing scales, and we can see that our algorithm DMAP managed to outperform both DPGESP and GMMAIs both in time and value mode respects. We also produced small scales and large scales problems. In the small ones, the agent finally didn't really outperform them because the GMMAIs is optimal. And in the large scales, we took problems that the other algorithms didn't manage to even have. And very fast for future research, we have both branches we can go in, different reward shaping techniques. And in the scale aspect, we can use online planners instead of the offline ones, which solve the POMDPs. So that's that basically. Thank you.